Alright, ladies and gentlemen, what we are going to be discussing in this lesson is pretty much one of the last things that we will be talking about as far as exponents and logarithms and how they're used. The last function that we're talking about as far as uh, anything associated with money is something known as an annuity formula. This is something that you might use when you're trying to not just save money, like if you get whatever amount of money that you want to save each month, you're not just like sticking it on your mattress or something. You're investing it into an annuity account where you're also on top of the money that you put in every month. It's almost like a monthly payment that you do, or a quarterly payment, or once a year, depending on what type of account it is. You're also collecting interest on it. So it's not just you setting aside that money each time, every month or whatever it is. It is whatever that money amount is plus interest that you accumulate over the course of the time that you have your account active. And one thing that we have kind of different in this function from our compounding interest functions that we've seen in other lessons is the capital R, where the capital R is just kind of replacing the ratio of the interest rate divided by the number of times something is compounded, whether that's daily, monthly, quarterly, whatever the case is. So let's go ahead and see how we use this particular function. So what quarterly investment amount is required to ensure that Larry can save $4,700 in 4 years at an annual rate of 8.5% interest compounded quarterly? Okay, well maybe this is something that, maybe Larry's a college student and at the end of his college career he wants to be able to buy a new car, and that's the money he's going to be saving for a down payment or something. Okay, so how much is he going to have to save? Or how much is he going to have to invest each month? So this 4,700, that is an accumulated amount that he's looking for. Here, the time is in years. We're compounding it quarterly, so N is also 4, and the interest rate here is 8.5%. So the function that we start off with is the accumulated amount is equal to the principal amount multiplied by 1 plus r to the nt power minus 1. And that is the whole thing divided by r. Well, what we're trying to figure out here is, well, how much money is he going to have to save? Or how much money is he really putting in to his account, to his annuity account, every uh, every 4 months, because he's doing it quarterly. How many times does he do, or every 3 months, I should say. What we're looking for is the principal amount. So for this function, because we have a lot of things going on with it as far as variables and numbers that we're going to have to substitute, what I'm going to do is I'm going to treat this as a literal equation, and I'm going to solve this function for p before I start substituting any numbers into it. So I'm going to get rid of the r out of the denominator by multiplying both sides by r, and I'll get a times r to be equal to the principal amount multiplied by all of this, 1 plus r to the nt power minus 1. And since the principal amount is multiplied by all of that, well, that means that all we have to do is divide, and we'll say that the principal amount will be equal to the accumulated amount times r, which is a ratio of the interest rate and the number of times it's compounded, divided by 1 plus r to the nt power minus 1. And there's a reason we're going to use this in a future example that we're going to see here. So it kind of makes sense to go ahead and just work this out as a literal equation. So here we'll say P is equal to, now we'll go ahead and start substituting our numbers in. The 4,700, that's the accumulated amount that he wants to have after 4 years. The R in this case is a ratio of the interest rate, 0.085 as a decimal, divided by n, the number of times it's compounded, or how many payments he's making over the course of the year in this case. So in this case, this will be 4 over, and then we'll say parentheses 1 plus that same ratio, 0.085 divided by 4 to the nt power. Well, n is 4, and time in years, oops, not t, but time in years is also 4. So you can, if you want to, you could just write 16 there for 4 times 4, and then we're subtracting 1 from whatever that number is. So this is going to be a good keystroke activity on your calculator. Make sure, do you want to do everything in one go? Do you want to do the numerator first and the denominator separate, or how do you want to work it out? But practice typing this into your calculator however you want to do it. And in this case, Larry is going to have to set aside $249.71 every quarter, every 3 months, in order to have his $4,700 amount that he's looking for, which is kind of a weird number, $4,700. But I don't know, maybe he has, maybe that's, he knows more about what he's doing than I do. I just know that that's what he's going to have to set aside at his interest rate, compounded quarterly, in order to reach his goal. So next example, Renee is tired of renting and decided within the next 5 years he wants to have $22,500 for the down payment on a home. A pretty reasonable amount. He finds an investment company that offers 8.5% interest, compounded monthly, and he begins depositing $250 each month into the account. Is this monthly amount sufficient to help him meet his 5-year goal? And if not, find the minimum amount he needs to deposit each month that will allow him to meet his goals. So I'm pretty sure by the fact that part B is saying if he doesn't reach his goal, that part A, the answer ultimately is going to be no. But we need to figure out what that number is going to be. So going back over the question, let's go ahead and identify things that we need. Here, time is 5 years. The $22,500 goal, that would be his accumulated amount after 5 years. Interest rate, 8.5%, pretty good interest rate. We're compounding monthly, so in this case, N is 12. And the $250, that would actually be the principal amount that he's paying each month into his annuity account. Okay, so it's not just like a one-time thing like it is with a savings account. He's budgeting this every month so that he has it to pay. All right, so part A says, will he make $22,500 with what he has right now? So let's go ahead and see. The accumulated amount is equal to the principal multiplied by 1 plus r to the nt power minus 1 divided by r. So let's just plug our numbers in and see what we get. So the principal amount that he's paying each month is $250. The ratio of his interest rate and the number of times it's compounded. In this case, his interest rate is 8.5%, so as a decimal, that's 0.085 divided by the number of times that he's paying it, in this case 12. And we'll say 12 here times 5, and if you want to, you could just write 60, and then we'll just say minus 1. Okay, so this is and let me finish it off here, over the 0.085 over 12. You can, again, this is a good plug and chug exercise. Can you plug all these numbers into your calculator and get the correct answer out? And in this case, Larry will have, after 5 years, $18,610.61. So unfortunately, no, he will not reach his goal, which that really wasn't surprising based on the way that part B said if not, but we needed to make sure that we could actually get the correct number why he's not going to make it. Okay, so let's try it again. Part B says, okay, well, Still wants to get into his own place in 5 years. His interest rate 8.5% is still what he's working with the bank is an annuity account. So we're going to figure out, well, how much is he going to have to pay into his account each month? So we're going to use our rearranged formula that we did in the previous example, where I'm going to say P, the principal amount, is equal to A times R divided by that whole expression 1 plus R to the nt power minus 1. And let's see what we get here to see what his monthly payments are going to be. So what he wants is $22,500 at an interest rate of 0.085, where he's paying 12 times a month into it. And so in the denominator here, we're going to get 1 plus 0.085 over 12 to the 12 times 5 power minus 1. And again, we'll just plug those numbers into our calculator and practice making sure that we can get them. In this case, what Renee is going to have to set aside for his monthly payments into his annuity account is going to be $302.25, which maybe that's something he can afford on top of what his rent for his apartment is now, car payments, car insurance, food, medical, living, utilities. I don't know, through an extra $300 a month, that might be a little hard to do. Maybe he wants to change his 5-year plan into a 6-year plan. I don't know, but that's what he is going to have to set aside. Maybe he can do it. Good luck to him. Okay. So the last things that we're really going to be talking about here are an exponential growth and an exponential decay operation. Exponential growth is something that is used to model populations of, well, whatever, whether it's bacteria or people. Exponential decay would be very popular examples are radioactive decay, maybe where medicine is, an antibiotic is, taking out, you know, bacteria that's causing you to have an infection, something where something is dropping over the course of time. Where Q is a quantity remaining of something. The way that we're looking at it is we're going to say Q over some period of time is equal to an initial quantity, which is a Q sub 0, multiplied by E raised to the RT power. Where now I want to make a note here on the R. In a lot of functions, if you just Google exponential growth and decay formulas, a lot of times you'll see that R represented with a K, where we're just referring to that as the constant rate of growth or the constant rate of decay. Our curriculum is using R to represent a rate of growth. A lot of other curriculums will use a K and they refer to that as a constant rate of either growth or decay. And in this case, T is whatever the measurement of time that they are providing you in the problem. It is changing from what our compounding interest problems were, where time was always in years. In this case, time is going to be in whatever units they provide, where that could be minutes, seconds, hours, years, whatever the case is. Time is going to be, we'll use whatever values that they give us. So here, again, very popular thing that we're doing, modeling population growth. After the wolf population was decimated due to overhunting, the rabbit population in the Boluti Game Reserve began to double every 6 months. If there were an estimated 120 rabbits to begin with, A, find the growth rate, or that constant rate, whatever it is. Sometimes it's called K, and we're going to refer to it as R. B, find the number of months required for the population to reach 2,500 rabbits. Now, in order for me to be able to answer part B, I have to be able to figure out part A first. I have to know what is the rate that they're growing at over the course of time, okay? So yeah, it's nice to say that they're doubling, okay, but we have to have, okay, let's give a percentage of it. What is that actually going to be for our functions? So here in part A, we're going to look at our growth formula, which is Q of t, the quantity over some period of time, is equal to the initial quantity, Q sub 0, multiplied by e to the RT power. And in this case, part A is telling us, we'll find what is that constant rate of growth. What is R? And since R is positive, that's what tells us it's going to be a growth model. So you're starting off with 120 rabbits. So you can say, well, in 6 months, you're going to have 240. And we're going to times e to the 6r, so 6 is the time that we're looking at. And what winds up happening is the very first thing you do in order to solve this problem is you have to divide by the initial quantity. You have to divide both sides by 120, which gives you 2 to be equal to e to the 6r power. Now, a lot of times, because you're doubling something, a lot of times people working these problems out, they'll just jump right to this and say 2 is equal to something. But if you want to do that, you're welcome to. Otherwise, just use a little bit of common sense. Say, okay, well, if I had 120, I'm going to have 240 in 6 months. So that's where those numbers are coming from. Now, this is why we have to have, again, a little bit of background with exponents and logarithms, because the variable that we're solving for is in the exponent position. The only way I can take it out of the exponent position at this point would be, since I don't know the number, I can't take the root of that, so I have to take the natural log of both sides. And in this case, I'm specifically taking the natural log as to, instead of log base 10, because the base of the exponent is e. So I'd say log base e, or I'm sorry, natural log of e to the 6r power. And according to our power rule of logarithms, we can rewrite this as saying natural log of 2 is equal to 6r times the natural log of e. And again, the primary reason why we want to say the natural log of e is because that just simplifies to be the number 1. So at this point, we can really just say I have the natural log of 2 to be equal to 6 times r. So that means r will be the natural log of 2 divided by 6. So if you type that in your calculator, natural log of 2 divided by 6, that will give you about 0.1155 as the rate, or as a percentage, we would say 11.55%. But that is we want to keep it as a decimal because it makes no sense to convert it into a percent if we have to convert it back to a decimal to do more math with it. So we have to figure out what that constant growth rate is in order to actually answer part B, where it says, okay, in part B, how much time is it going to be before it takes me to get the 2,500 rabbits? So using our same growth model, Q of t is equal to Q sub 0 times e to the RT power. In this case, we're going to say 2,500 rabbits, because that's the number that we're looking at, is equal to the initial quantity of 120 rabbits times e to the 0.1155 t, because we know the rate now, but we don't know how much time it's going to take to get 2,500 rabbits. So we'll start working this one out the exact same way that we did in part A. Divide both sides by 120, and if you say 2,500 divided by 120, it doesn't give you a very nice decimal. So we're going to simplify it as a fraction, which would be 125 over 6 to be equal to e to the 0.1155 t power. And at this point, we're at the same place that we were in part A, where the variable that we're solving for is in the exponent's position. So the only way I can get it out of there is by taking the natural log of both sides. So I'll say the natural log of 125 over 6 is equal to the natural log of e to the 0.1155 t power. And using our power rule of logs and the fact that natural log of e is just equal to 1, we can at this point say the natural log of 125 over 6 is equal to 0.1155 times time. So divide both sides by the 0.1155, natural log of 125 over 6 divided by 0.1155, and that will tell you how much time in months, because that was, they're giving it to us every 6 months, so that's what our answer will be in as well. So depending on whether you used an exact number or you rounded your decimal at some point, like if you saved the 0.115 number on your calculator, or if you just typed 0.1155 on your calculator, it's not going to make that much of a difference, and we'll say 26.3 months in order to in order for the population of rabbits to reach 2,500, which seems like an awful lot of rabbits. So I hope you don't have any gardens there, because your lettuce and carrots aren't going to last long. All right, the last examples that we're going to be looking at here, in this case, well, we looked at an exponential growth model, so now let's look at an exponential decay model. So the radioactive element, sodium-24, has a half-life of 15 hours and is used to help locate obstructions in blood flow if the procedure requires 0.75 grams and is scheduled to take place 2 days from now. What is the minimum amount that must be on hand right now in order to have enough for the test in 2 days? So exponential decay follows a very similar function to what we did for exponential growth. We're going to say the quantity over some time is equal to the initial quantity multiplied by E, but in this case we're going to say to the negative RT power. And the fact that the constant rate R is negative, that's what causes it to be a decay model rather than a growth model. Now, in the last example, because it said that we doubled something, we could just at some point just say that 2 was equal to e to the RT power. So you might say, okay, well, if I'm saying half of something, can I say half is equal to e to the negative RT power? And essentially you can. So what we're going to do is we can say half of something, well, whatever we started with, if we have 1,000,000 of it before, well, now we have half of that. If we had 10 of it before, well, now we have half of that after so much period of time has passed. It decayed. So we can say E is equal to, or 1/2 is equal to E to the negative RT power. And using the properties of exponents, we can rewrite the right side as 1 over e to the positive RT power, take the reciprocal of the right side, and essentially at this point we simply have a proportion where if I multiply, cross multiply both sides, that would give me e to the RT power is equal to 2, and if I need to figure out what the rate is or the time is, I would say take the natural log of both sides. And in this case, again, using the power rule for logarithms, what we're going to get is that r times time is equal to the natural log of 2. And if I want to know time or the rate, which usually we have to start by finding the rate, I can say the natural log of 2 over whatever the length of time is. Okay? So in order to figure out, well, how much am I going to need, this one doesn't it doesn't specify, it doesn't specifically come out and say, well, figure out what the rate of decay is first, but we have to figure out what the rate of decay is. There's no way around it because they're not telling us what the rate of decay is. All we know is that the half-life is 15 hours and I have to give the test in 2 days and I need this much of the material. I need 0.75 grams. They're not telling us what is the rate of decay. We have to figure that out. And so that's why we kind of want to look at all of this stuff here on the right to see, okay, well, how do I figure out what is the rate of decay? So to figure out R, in this case, we'll say R is equal to the natural log of 2 divided by, in this case, the time of the half-life is 15 hours. So let's say divide by 15, and the rate of decay in this case is going to be somewhere in the neighborhood of 0.0462. Okay, so that's going to be the rate of decay. So we want to know how much do I have to have now in order to have 0.75 grams of it later. So the 0.75, that is what that's what we need. That's going to be the quantity over some time. And we're looking for Q sub 0 times E to the negative 0.0462 power times, in this case, the time, how much time is it going to take before we take the test? In this case, it's going to be 48. And so now we can divide everything by the e to that power. And I'm not going to try typing that into the calculator for a decimal number. We'll just say 0.75 divided by e to the negative 0.0462 times 48 is equal to the initial quantity, and type that into your calculator, and the initial quantity that you needed of the sodium 24 is going to be to the nearest hundredth would be 2 decimal places, so let's say 6.89 grams. And that is how we would have to work out our exponential growth and decay. Sometimes they're real clear, like we saw in the first example with exponential growth. They say, hey, you got to figure out what is your constant rate of growth. But in this case, they didn't come out and say, hey, you have to figure out what is your constant rate of decay. You have to understand that if I'm looking at an exponential growth or exponential decay model, unless they give you that, the first thing you have to do is figure out, well, what is my growth rate or decay rate. So, and also that for our curriculum, we're using R for that, but in a lot of other ones that I've seen, they'll use the variable K, simply talking about the same thing. So again, this is pretty much wrapping up what we've been talking about for compounding money problems and exponential growth and decay. So if you have any questions about anything, make sure you have them written down as we go through the presentation, and bring them to me when you see me in class, or come see me in tutoring to get you any answers that you have cleared up. But in any case, thanks for watching. I hope you learned something. We'll see you in class soon.